Hello everybody. Today we're going to have some applications in Simulink. We will look at them. Now, as you know, Simulink is a toolbox of MATLAB where you can drag and drop some blocks that are functional. In a way, you're basically avoiding to code everything using MATLAB. You can use some visual tools, and since it's visual, most of the people prefer to use Simulink. It has some advantages, it has some disadvantages, and we will see that during these tasks of today. Well, first of all, a state space realization is given below. You can see that this is a system model, basically, which has a typo in it. This should be here. So it is x dot equals ax plus bu, not this way around. I will correct this. And use one of the OD functions. Before we get into Simulink, I will show you that basically it is also possible to code these things without Simulink. So the first task is about that. You can use the OD function. There are certain OD functions, and you can get the step response of such a system, for example, and plot the states on a figure. Now, let's go to MATLAB, and one of the OD functions that I know is help. Let's call help, and it is OD45, which is Runge-Kutta, which is an algorithm that solves differential equations, basically especially the non-stiff differential equations. And we have this here, which will help us in coding this. Now, let's look at the system. We have A. Let's write A equals 1, 2, minus 3, and minus 4. And we will have also B. Let's look at that. This is 1, 0. And that's basically it. We will acquire the states x1 and x2. Now, usually you would go ahead and use Simulink. We will do that in B, but first we will try to solve it here. Now, before you do anything, basically, you have to have a ODE function that will be used in the algorithm that in order to get the differential equation solution. And then we will have some time span and initial values. So we didn't talk about initial values, so they will be 0. If they're not provided, you can feel free to assume them 0. And then we will look for the step response. That means that we will have an input that will be ut, that will be a step function. Now, as you can see, it is fairly easy to code it if you want to make some changes in your code. It might be the case that you want to change one parameter here. That's not easy with that much easy, at least with Simulink, since you most of the time hard code your values there. And using a for loop, as far as I know, if I'm mistaken, please correct me. But as far as I know, you cannot use a for loop. What you can do is you can provide a parameter and then define it in MATLAB and then call Simulink externally. But as I've talked about that, we will see that. Now, I don't know, about maybe 5 seconds should be enough. I'm not sure. The initial conditions, let's say x0, should be 0 and 0. I'm not sure about the structure about that. So this is x0. We gave time. Now we need a function. Let's say dynamics in this case. So you can use this. So this will be y or x in our case, and time out. If you don't want to get that, you might also type it like that. Since I've provided time, they should give me the same time back. maybe let's say T2 and compare that. If it's the case, we might omit this parameter. If not, we will use T2. So now the only problem here is to define a function that defines our a differential equation. In this case, we have a state space realization. So this part is not that pretty. So let's try to make it as much pretty as it is possible. So, well, basically, in MATLAB, you can go ahead and open up a new function here, and you can just do whatever you want here. Maybe I will show you both ways. Let me do that instead of this here. Let me show you this way first. So I might have a dynamics, and the OD function expects to be able to use time and the state itself. Now I will take my definitions and I will paste them here. That's the reason why I'm showing you this method here. And basically what I will return is dx, the derivative of x, and this return statement should calculate ax plus b times u. In this case, u is 1. So I can get away with this here for the moment. So, and this will be called dynamics. And I don't use t, but I should define it as far as I know. Now, if you are passing a function in MATLAB, you cannot do it by just giving the name, because if you do this, MATLAB assumes that you're trying to call this function. So if you want to pass a function as an argument, then you should convert it to its address or its pointer, as in C. You just you can just use this @ sign here, and this will help you out. So using Control Alt and Q, you will generate this here, and this will convert this function to its handle and will pass it to the OD function. In order to be sure if it's working or not, maybe we should go ahead and run this here, and it says it should be a column vector, so maybe correcting this here. Maybe the time vector can be an issue too. I am not sure. Maybe we should read it. Dynamics must return a column vector. As far as I know, it does return a column. Oh, I did not. This is not how B is defined. So, okay. Now you can see that I have the states here. I am curious about T2. It seems to be the same, only the structure is not the same. It is the same, so I can bypass this T2 here. Now, let's generate a figure, and let's go ahead and hold on, grid on. Let's plot this T, and since the structure of X shows me that I should use all the rows and the first column for state 1, let's say line width of 2, and then display name x1, and maybe I should also look for the second state, and this should be x2, x label, and then y label, and then states. Okay, now basically I'm using the OD function and I'm acquiring the step response, and you can see maybe legend show is also helpful for which state is what. And there you go. Basically, this is the response that we are looking for. And I've used OD45. So this is the response of a continuous differential equation. It is also possible to use the differential equation version. As you might remember, it is possible to use these relations. Again, this is not the correct way of displaying this, but assume that the x1, x2 vector is here. You can just work out the original second order differential equation, and then you can go ahead and go into dynamics and define your differential equation here, the right hand side of your second order differential equation, and it will be the same. So since we are control engineers, most of the time we might want to prefer this state space realization or representation. Now, as it is also possible in our case, it is also possible to use it in one line. So sometimes it becomes more handy to define a function on the fly. So how can I do that? Well, basically, what I need to do is I need to create a function. So this is a bit messy, but what it does is basically it returns the reference that has 4 input arguments with t, x, a, and b, and this line of code will be just one line of code. If you are familiar with C++11 or some advanced C methods, you will recognize the lambda function, which is a anonymous function definition, or in C# you have that kind of function type too. So this is the way of MATLAB. This is the MATLAB version of defining an anonymous function. Since I am concerned with linear systems, most of the time the on-the-fly method is more preferable for me, because what I do is I just type in a times x plus b times 1, since I'm most of the time looking for the step response. So in one line, what I did here is I passed t, x, a, and b, and my definition here is basically equal to dx here, but I don't need to even define this dx variable. I can just multiply a and x and add b times 1, and this will be the column vector that the OD function will use. The only problem here is that I have to recast this function, or I will redirect my input arguments in a way that I'm calling the function itself. I'm passing both these arguments, because remember that the OD function only knows 2 arguments of this. It will pass t and x, and you will just need to provide a and b. So the point where I'm providing a and b is here. So maybe if you don't want to get confused, I might also change it to a underscore b underscore. So if you look at these 2 lines, or maybe let's include a and b too, what I'm trying to do here is I'm giving the form of my differential equation or state space realization here, where a and b are placeholders, and these will be provided as arguments, and then I am giving t and x. So you can also copy these values here and paste it here if you are just concerned with this, or if you're just considering this system. But if you want to change it later, I might change it here and everything will be updated. So that's the reason why I've constructed line 9 as it is now. And here I am converting my 4-argument function by wrapping another function into it, around it, so that it has only 2 parameters, and the other necessary parameters are given by me, are provided by the user as a and b. So this wraparound and doing stuff is a messy part, but does the job as it should be. It's kind of, as I've told you, a little bit interesting, And let me maybe show you what the output looks like. If I do this, you can see that this is a function handle with value this. So again, what is the function? It is another handle, and if you type in function, you will get that this variable has 4 argument anonymous function, which is equal to ax plus bu, basically. So this function lives in this function with directed parameters, and a and b are values. That's basically it. So I like this method more because sometimes I have a state space realization and I will just provide the function in one line, and defining extra files with functions may not be that necessary. So this is the first task here, and it says that we should repeat it with Simulink. I have opened up MATLAB but not Simulink. Maybe I should have typed Simulink before because it needs a little bit time to initialize, but interestingly does the job. Now I will repeat the exact same thing here, and in Simulink you will just go ahead and type what you need, and it will give you some options here. And the thing that I'm going to use is a state space. So I will embed it directly, but you can also call it directly A, and it will look for the workspace. The new integration, by the way, shows you, I guess, some values. I'm not sure. It comes from the workspace and shows you you have defined B already. You might want to use this one, and you can use it, but sometimes it's also a good idea to embed it directly. So keep in mind that we don't have the C and D matrices for a state space realization, but this doesn't mean that we don't have them. Basically, the question didn't define them, but we know what we want. We want the states, so this means that we can define our own C and D matrices if they're not given. And if I want to look for a state space system step response, and now since I want to inspect the states, I should give an identity matrix here of 2, and then a 0 vector or matrix that is 2 by 1. Why is it 2 by 1? If you think about it, you will see that I have only one input and 2 outputs. And D is the direct term from the input to the output. So basically, if I have 2 outputs, it should have 2 rows. And if I have one input, it should have 1 column. So 2, 1 zeros. That's the reason behind that. By the way, if you are dealing with state space systems, let's say, and in control system design, you are trying to design a state feedback controller and an observer, let's say the Lundberger observer, then it is a good idea to keep in mind that you should use the state space always as shown here. So never actually provide C and D here. Never. Just make it identity of the size of your matrix A, and a 0 vector accordingly that has rows and columns that fits the direct term, and leave it like this. I will tell you the reason in a second. So let's take a scope and let's connect it directly here, and let's take a step function and let's connect it here. So this is the same simulation here, but we have some interesting style in our scopes. That's the reason, and I'm not really sure about this, but my prediction is that it looks like an oscilloscope, and that's maybe the reason why we have this, because a scope is more like an oscilloscope, something that will would have been in the laboratory. So that's kind of the look and feel here. I'm not sure. Well, here somewhere is a style editor that I like to use, and most of the time I change the figure color to white. I don't care about that. This to that, and access colors to that. I'm not sure. Okay, this was white. There we go. A more like a better view. If you're generating plots here and want to use them for presentations and actual presentations, what I mean by that is if you're in a classroom and you will use a projector for this, I highly recommend you that you go ahead and change the styles as I'm showing you here, because having a black background on projectors doesn't work that much as expected, because the pixels that are black are not generated via light, but they dim those pixels, so there might be a quality issue. But if you have a laser high-tech projector, then it's not that important. But most of the time, white background is used because white will be generated by projecting light through those pixels, so it becomes more clear and readable. But it depends on your projector, basically. But it's always a good idea to have a white background. If you're printing out, that's also a good idea. If you're printing out black, you will use too much ink, so etc. etc. Now, the first challenge, I don't mind the colors. Maybe we should change them, I don't know. Let's have channel 2. That should be line width. This is line width. Basically, the thing that I'm always updating here is also here. So if I hit run, I see I have basically the same. The only difference here is that it has a 1 second step time, so I can, if I want to, but not that necessary, I can change this step time into 0, so it will directly start with at t equals 0. So I've generated basically the same figure as shown here. Only the colors are not matching, but it's the same. And this is a 5-second zoomed version here, but you can see basically the first state approaches 2 and the other one minus 1.5, and they seem to be the same. So this is how you will use Simulink, or how you could use the code. And you can see that this is not that much of a code, and it's not that hard. It's up to you. You can use whichever you want. The only drawback in coding this whole thing is if you have a structure that is highly complex, then you might opt for the solution with Simulink. If you have a basic structure and you're looking for parameterization of stuff and changing some aspects of it and repeating this simulation over and over again, then this coding will pay off most of the time, because it's way easier and more suitable for your needs. Now we've done both of them. Now we can use Simulink Mux blocks and export the simulation data and repeat A. So what we mean by A is that you should export the data and use Simulink, because sometimes generating reports will be much easier using MATLAB, and you want to just run some simulations and save them. So that might be the case. Before I transition into that, let me show you how you should use the state space most of the time, if you're concerned, or if you have to consider the state space variables, those x's, those states. If you need to use those states, then don't ever plug in the C and D values, but go ahead and pick a gain and change this gain to, as you can see, this is an element-wise gain. So this means that this is a scalar gain, but you might want to change it to matrix K times U. So you can go ahead and type in the gain as a matrix 1 0. Let's say 1 0 is a matrix that you need. And if you have D, for example, since we are in SISO, the gain D can be left as it is. You can go ahead and construct your output outside the state space here, because this is more likely to be more effective, since it has the states here. So I will have the our states are here, so this is a 2x1, and you will construct the, let's give the sum here, let's make it change it a little bit. So you can just go ahead and construct the cx plus du term outside of the state space, and if you connect this, now you have the output itself, not the states. But if you need the states, you can also have them. So basically, let me go ahead and change the style here again for the third channel. I don't meant to do that. So let's go ahead and look for the channel. Okay, why don't we have this channel 3 now? Let's change the signal ports. You can change the number of input ports here to 3 or 2 or whatever you want. I will change it into 2, but actually it is 3. Since this is a 2x1 vector, it will add 2 more data into this. I'm not sure if I am able. Nope, still not able. Let me run the simulation and then change it. Basically, sometimes you have to run the simulation in order to get updated, and you can see now that the second stage should be this color doesn't is not that appealing. Maybe this one is better. So we can see now I have the states and the output that is necessary. So basically I could have used C and D in this state space, but then the problem is that I am not going to be able to use those states. So never ever plug in the C and D values into a state space. Just go ahead and pick 2 gains and one sum element and use them to generate the output outside of this, because sometimes, and in control design, that's most likely what you will do. You will just go ahead and copy this and then add some extra term to this in order to use, let's say, an observer here. You will connect the same input here. Let's connect them. So, but probably you will use an error feedback here. You will take the difference of those. Let's plug that in. Let's make it, depends on that, but I don't remember why is that a sum now. I messed up the shape, but there we go. Sometimes you will go ahead and take the difference of this, especially for observers. It is a good idea. Then you will have an observer gain, and something like this here. And then this will, of course, be a, let's say, something like this here. I'm not sure. And then you will add this into your input. Since this is the error term, you will have another summation here. And then you will have the input, something like this. And then you most probably will compare the states. So if you use it like this, I have the states here, I have the estimated states here. So basically, this is the best way of defining the observers for linear systems. I have to connect this one to, I guess, du. I'm not sure. I'm just, this part may change, but you get the idea. What I mean is, if you never ever use C and D as it is, you are able to use these as basically integrators and some summations, and this is reduced to just one block. And you can then give some inputs, and you will have the states, and use and manipulate those states as you wish. A little bit more flexible. So using just integrators and constructing the system that way for the observer or for the original system is most of the time the choice by you, but I highly recommend this version here because it helps out and is more flexible. Now, the only thing that was requested, I wanted to just talk about this. That's it. We don't even have these here. So it says that use the mux blocks and export the simulation data. So why do I have to use multiplexers? This is basically something like a multiplexer. I don't know what it really was, but I might want to look for the reference. I might want to look for these states and the output. Whatever I want to export, I will combine them into just one thing here. And instead of a scope, I will use something called to workspace. It is possible to use the workspace, or there's also a to file version, which is basically the same. You will give it a file name, and it will save a .mat file. Now, if you connect this here, it will use out.simout here as variable name, and everything is like that. You might change it to array and time series, depends on that, but let's use array since that will have minimal data in it. So if I run this, I will get a workspace variable in the workspace, and you can see now I have out here as simulation output. Let's look at what the out looks like here. Let's comment this all out. By the way, if you have clearance, you'll see this will obviously be get erased, so get rid of that part. Now you can see that I can get the sim out variable, which is 57 times 3, which means that I have 3 signals embedded in here. First two of these, because I know the connection here, are the states, and then the last one is the reference. So keep that in mind. Maybe you will go ahead and use out.simout, and you will see that this is basically a vector. So if you want to have x here, you might go ahead, let's say temp, or let's say data. So we store this matrix data in a data variable, and then if I want to extract the states, I need to use data and all the rows, just the first 2 columns here. And if I want to look for the reference or the control input that I've used, I might go ahead and use all the rows, but just the 3rd column. And then I can go ahead and use this here instead of my scope or my code. I'm just going to use this data, and I might also add a plot where I have the input reference plotted to. So maybe I will give it a color of black. So that's it. Now if I run this after running the simulation, by the way, I need the time data. So was it out? Yep, out.tout should be my new time data. I didn't define that. T equals out.timeout. No, T out. 57 to 1, maybe. It's okay, but most of the time we will use the transpose of this, but now it's okay. And you can see now I have the simulation data plotted here. This has an advantage since I can go ahead and use this print statement. I can give it a name, let's say result.png, and I can provide the renderer as the PNG, give it a resolution of 150 dpi, and you will see that this will be used to generate the file that I can see here, and I can open outside MATLAB, and it will open me a result.png. So if you're creating a report, 150 SADPI might be enough, but if it's a poster, if it's something big, then maybe increasing this resolution is important. The DPNG, you can change it by using the help or documentation on this print function, but this is most of the time more than enough for basic reports. Now, this way you can generate nice plots. So having a workspace thing gets rid of the whole nonsense about the scopes. So I highly recommend you to use this workspace or to file. You can also use files if you want to use these outputs later on and want to examine them. So I highly recommend this method. You can just go ahead and use it. It's very, very helpful. Now, use Simulink and MuxBlocks and export the simulation data and use a p-type controller in closed loop, plot the reference, error, control input, and output signals. This is basically a modification of C, so let's quickly do it. It said that use Simulink and MuxBlocks and export the simulation data and use p-type controller in closed loop. So I don't remember what the transfer function looked like. You can just go ahead and get rid of the state space, for example. Just maybe use a transfer function, one s plus one, and if you want to use a p-type controller, the p-type controller is a gain, so just use kp here, and then you can connect this here. Then you need a sum, which will generate the feedback. So the only thing here is that you should have a negative feedback, which, by the way, is not here. I'm sorry. It should be in the input since it's a feedback, not feed forward. So you will have this feedback, and then you will be applying this input here, and then for the simulation output. Now, let's give some names here. This is the reference. Now, this is the output. So the controller, this one, generates U, which is the input of the system. So it generates the control input from the error. And this is the error. R minus Y gives E. E times KP or FS, or E applied to FS gives U, and U applied to the system will give the output. So, and let's use a mux element here. And let's count our variables, R, E, U, and Y, which makes 4. So basically, you double click this and hit 4 and enter it. Now you have 4 possible inputs. Now I want to rotate this so that I have a better routing. I've connected this to the reference, and then the error, and then maybe the control input, and then my output. So that's it. So I'm not sure, but am I able to change the whole color of this? Was that possible? I'm not sure. Format, font style, foreground color, maybe blue. Just this part, not the lines, but whatever. So basically they will be combined into just one data structure, one array. So double click that. This was an array. Okay. Now I have to modify my code a little bit, since my first one is now the reference itself. So let's call this 1, and then I will have the error, which is the second one, then the control signal, which is the third one, and then the output, which was the last one. So first I have to run the other one and then the other one, but let's change this into reference. Let's change this into output. Let's get rid of these. Let's maybe create another plot here. I might get rid of this. And in the second one, I want to see what my error and what my control signal is. And that's basically it. So first I will save this and run this here. So I did run it. So let's run this one here. There we go. But okay. There we go. Since I have used gain 1, it's not possible to see exactly the effect here. Let's run it, and there we go. Better. So I can see now that my output has this shape, and that my okay, the legends are not as they should be. This is the error. This is the control signal. This is the reference. This is the output. So using this method by combining the coding and Simulink together, it's handy. So you can just go ahead and make some changes in the visual side and just run the MATLAB code, and you don't have to repeat the whole simulation. So you can see now that my error and my control signal are basically proportional. They are related to each other. The control signal is twice the error, which makes sense because I have a static controller, and that controller has gain 2. So I might want to increase this. I might want to use 3, and then run the simulation, and then run this one, and you can see that it kind of applies more control signal, so and stops at a higher point for the steady state control value, which means that my steady state value increases. So it will approach the one line. So I will have approximately, not exactly, but approximately 10% steady state error. Approximately, because 10 divided by 11 is the actual error band here. So I can see that higher and higher control signal will give a better, let's say, response. But you can see that you're restricted to the shape of the error. So basically, I'm just multiplying this error with a constant, and that's it. I have no transient, no dynamic behavior whatsoever. But if I would have changed the controller structure, if I would have used, let's say, a PI controller or a PD controller, at least I would have had the opportunity to combine the error and its derivative or its integral, so that I have a different behavior. So I don't have that freedom here, because this is the most basic and simplest controller available for me, namely the static gain controller. Now, use Simulink to apply sine wave to a system, calculate the amplification, plot the amplification versus the frequency. Now, I'm going to skip it, and I'm going to show you what the solution looks like. Let me just get this window here. Now here we have some codes, and these are explaining basically the same thing. You have A and B, you have this OD, and you can see that the task 1 is repeated here. You have C equals this, D equals this. This should be 0, I guess. I've copied and pasted, obviously, but didn't change the 0 here. And so you can get basically the states. For C, use Simulink. You can save it into a file. Also, you can go ahead, and I have a different video on this, so I'm skipping this for that reason. You can also use Open System, the sim, to just call Simulink behind the scenes, so you don't have to actually open and click it. You can just go ahead and use this piece of code, which is also not that difficult. You have to define your system name here. keep in mind that this name is used here to set the values of A, B, C, D, namely the properties that are available. So this is the same, this is the equivalent of clicking and typing in A, B, C, and D. So these are setting those parameters of the block that is shown. And I can also change the solver type. I can change the start time, stop time, whatever I want. And running this line starts the simulation. I am not bothering with the input output since this is going to be saved into test.mat. And I can, once the simulation is done, I can just load this file via this code and then the same thing that I've shown you. Basically, this method is very useful if you want to repeat your simulations. So you can go ahead and define the structure that you have, and then you can externally define your parameters that might change, and then you can just run the simulation over and over again with different parameter values and get the data and plot them on top of each other. For example, you have this here that I've shown you, the structure here. You can load it and you can change the numerator, the denominator, and you can also change the gain here. And what I mean here is you can just use a for loop that probably will start somewhere here. You can start the for loop before this line and change the gain in a for loop, and you can just plot whatever you want on top of each other, or you might generate a table of certain data of the simulation and then just live with that. Now the last one is to connect a sine wave to a system and then to get the data basically. And it helps you so that you can go ahead and look for, let's say, the gain, the amplification, the phase. You can, since you have all the data in the workspace, you can just go ahead and try to calculate some complex stuff via code. So basically, this is how you can use MATLAB Simulink a little bit more effective, hopefully, and a little bit more automized, let's say. Hope that this lesson was helpful for you. See you in the upcoming lessons.